you should recall that for simple harmonic oscillator, the maximum velocity is omega times the amplitude, assuming that we have the standard equation, that is that the position or the displacement from equilibrium is A times the sine or cosine of omega t. Okay, so again, our maximum velocity is omega A, which means our maximum kinetic energy is 1/2 m times the maximum velocity squared. Maximum velocity is omega A, so we get kinetic energy finally equal to 1/2 m omega squared A squared. That's the kinetic energy of a simple harmonic oscillator. The total energy of a simple harmonic oscillator is just its maximum kinetic energy, which is equal to its maximum potential energy. Most of the time the simple harmonic oscillator, almost all the time the simple harmonic oscillator is oscillating between maximum potential energy and maximum kinetic energy with some mix, but the total is always equal to this maximum, which is equal to this maximum. For a sine wave in a string, let's just consider a sine wave in a string, every point in the string is in simple harmonic motion, isn't it? Okay? If you've got a sine wave traveling down a string, every point is oscillating back and forth in simple harmonic motion. If the tension in the string is t, then of course velocity is the square root of t over mu, and what we're after is an expression for the total energy in the wave. So, or the total energy transmitted by the wave. And so let's think about this. If you have a wave moving at velocity square root of t over mu, then at time t, the wave front will be somewhere along here. The wave is traveling down some assumedly long string. It's just gotten to this point at some time. And then a time delta t later, it'll have moved an additional distance v delta t. Now, what's happened here? The mass in that distance v delta t has been put into simple harmonic motion. It's not all in the same phase, but every particle of the string between here and here is now in simple harmonic motion with amplitude A. Well, maybe we better zoom in on this just a little bit. Okay, so we see that in time t, or at a time t, the wave is here. At time t plus delta t, it's moved a distance v delta t, and we have a mass. That mass is just mass density times v delta t. And that's the mass that's now in simple harmonic motion. So that there's new energy. Okay, so in time delta t, the mass mu times distance v delta t, mass per unit length times the length of string that's now involved, is now undergoing simple harmonic motion that wasn't before. And there's therefore a new energy, which is 1/2 the mass mu v delta t times omega squared A squared. Because remember that the kinetic energy was 1/2 m omega squared A squared. Every particle, every bit of that mass mu v delta t is in simple harmonic motion with amplitude A and angular frequency omega. Therefore has this energy. The power will just be the new energy formed, or the new energy transmitted in time delta t divided by the time delta t, and that's just going to be this same expression we've got here but without the delta t. If we substitute the square root of t mu for v, or t over mu for v, and simplify it, okay, and the algebra is very simple, you should do that, we just get this expression. So this is the power that's being transmitted by the wave, and that's how much power we need to transmit that wave. If we've got a motor or something creating the wave, the motor has to have this much power.